chapter for a quest right before Thanksgiving break, right? I think it was Thursday, and then we went on break. No, then we started this section on Friday. Okay. On Friday, we talked about ridiculousness, but we did talk a little bit about math, but just not a lot. And do you guys remember what happened when a pebble goes into a pond? A ripple. What did I talk about? What was I introducing? The idea of a wave, and we talked about other things that move in wave-like patterns or behavior. Sound waves, light waves. The pendulum, good, talked about the pendulum, about how it would be like displaced, which would be going far away and then back to equilibrium. And all of that was leading up to sines and cosines, because sines and cosines look like what? Waves. Yeah. Now, we talked about how they're kind of like ideal waves in that they keep on going the same high and low forever, and that's not really real life, right? A ripple would eventually get smaller and smaller and smaller and then level out. But at the foundation of any wave will come a sine or cosine function. And the pendulum doesn't even look like a wave, but it does go like far away and then come back to a middle and then far away, and as you graph it with respect to time, it would look like a wave, like a sine and cosine. But then we were like, okay, well, sines and cosines, yeah, they're waves, which are kind of practical in all sorts of different models or different behaviors or different movements, motions, etc. And so we're going to need these guys to model that, or you're going to see these guys in future, I don't know, physics classes or future statistics classes or future chemistry classes. You'll see sines and cosines, they'll be there because they do model this wave-like or this apart from an equilibrium and back, this cyclic behavior. But they're complicated because they have 5 key points and not just 3. We've been usually doing a line needs 2 points, but a parabola 3, and almost everything else that we've been doing needed 3 key points, but these guys need 5 key points to get from the beginning to the middle to the opposite side to the middle back to the beginning. Whatever it is, beginning and then away and then beginning. And we call this middle equilibrium. That's one way of talking about it. But long story short, to make it practical, we're going to have to define by itself, but with transformations, and it can get bad, and that's what this page was for. Because we could get like vertical and horizontal shifts. We could get vertical and horizontal dilations. We could have it stretching and compressing with different periods and amplitudes and all these snazzy terms, which we're going to talk about a little bit more in a second. But for right now, let's just take this page, having identified all the different little letters that are up here, or at least use them. Let me see just 1 second, though. Can you guys grab out a colored pen or highlighter? If you haven't yet already. We usually use one in class, so it shouldn't be too crazy. But if you're looking at each of these, the sinusoidal axis, y equals d, it's just this variable right here, or this number right here. The amplitude, the max or the min, the amplitude is how high, which is just going to be a as well. That's just this one right here. The initial point, it's the whole thing c over b, so as long as we get it written the right way, it'll be this whole piece right here. The period is what's weird, though. The period is the awkward one, because the period one doesn't just use b. B is inside another formula. So he's the weirdest of them all, because with d, with a, with c over b, each of these, the actual quantities are used kind of on their own, but the one that is a little weird, if I were you, I'd definitely put a star next to it, is going to be the period. Because you actually are not going to see the b itself in the graph. We're going to use it. It's going to be used in something, but period is the awkward one, so we're going to actually leave him till last. We're going to work our way through the equation, identifying who's this guy, who's that guy, who's this guy. Then we're going to come back to the period and say, okay, you're the awkward one, you're the weird one, what do we do with you? But before we do that, question. Does this make you guys think of anything? I don't know whose this is, but I'm going to use it. Not hangman. What do you mean, Matthew? Remember? Maybe Maybe. That's more like what we're going to do today. Maybe this would make it a little bit more obvious. Didn't you used to have paper that looked like this? What? Really? Wasn't that long ago, was it? Oh. And then you would have something like this, right? And what were you supposed to do with this? You're supposed to trace, and so you're supposed to trace them, and then like they disappeared, and what were you supposed to do? Like write them on your own, right? And you would have the uppercase letters, then you would also have the lowercase letters, true? I'm a horrible elementary teacher, you can tell. Anyway, you have to trace it. We're going to kind of do something like this today. But we're not going to be putting letters in like handwriting lines. You guys have been there, done that, and most of you can actually form your letters. A few of you need to keep working on that, coming back, or slow down and not write so fast. Make it legible for anyone who's reading your handwriting. But coming back, most of you don't need this. But it would be helpful if we could figure out a top and a bottom and a middle for our wave. A top and a middle for our wave. Because the waves go in between tops and bottoms, maximums and minimums, and pass an equilibrium. We're actually going to kind of do this, but with those. So let me show you what I mean. Sinusoidal axis. Sinusoidal. What's the sinusoidal axis in this graph? Or in this equation, I should say.
Y equals D.
Yeah, y equals d, but what's the actual number in this example? 4. So what we're going to do for the sinusoidal axis, every single time, it's going to be the first thing that we do. The first thing that we do is identify y equals 4. So we're going to go ahead and come to our graph, and we're going to put a horizontal line at 1, 2, 3, and 4. This is going to be the center, or the equilibrium of our wave, like this one. It's going to be the center or the equilibrium of our wave, like the middle line on the handwriting paper. So there's our sinusoidal axis. There's our y equals d, but in this case, d is 4. Now, amplitude. We talked about this on Friday, amping it up to make it louder. What happens to the waves? They get stretched, or if you're making it softer, they get compressed, which makes sense. It's multiplication. Now, amplitude's a little bit weird. It doesn't actually look at the plus or minus. We'll come back to that in just 1 second. Amplitude is literally just the 3. So far we have our sinusoidal axis is at y equals 4. We have our amplitude at absolute value of -3, which is just the positive 3. And that means how high, how low is our wave going to go? 3 up. And more specifically, what I just did was 3 down from the middle, or from the side. Let me try to make this right on. Now, I do dotted on the top and the bottom. I don't do like the handwriting lines with the solid, because this technically isn't the graph itself. This is just the boundary for the wave that we're about to do. But from that equilibrium 4, going up 3 and going down 3 will get us the amplitude we need, or the height and the depth that we need. Because amplitude is technically how high, how low the wave goes. From the equilibrium, it's not the entire high to low, it's the entire top to bottom. What's the distance from the top to bottom of this wave? 6. 6 would be the entire distance from the very top to the very bottom. But this number, the amplitude of 3, is how far the wave stretches away from the equilibrium. So where am I at right now? 7 and 1, right? Okay. Which, if we were given a picture, we could actually, if we could see how high, how low the wave goes, we could say 7 minus 1 is 6, cut that in half, 3. We could go backwards from the graph also. We could see the center of 7 and 1 is 4. That would be our sinusoidal axis. You can go backwards from pictures to graphs. Or I should say from graphs to equations, not just equations, to graphs. Now, what's the next thing we're looking for? Well, you would think period, but remember how I said he was a tricky one? We're going to leave him. So we're actually going to pop down here to the initial point. We're going to check out cosine. So we're going to look at specifically this point, and I'll talk about where this comes from in a second. But we need the c over b. Well, here's where it gets a little tricky. You guys have to look at how the equation's written. So for instance, this way that the equation's written with cosine of parentheses 2 pi x plus 4 pi. Does that look like the first equations or the second equations? What do you guys think? Yeah, how can you tell though, Matthew? Good. There's a constant being multiplied by the x inside the parenthesis rather than a constant being factored or having been factored outside the parenthesis. Now, who are we looking for? C over b. There's two ways of finding C over b. One way is to figure out, oh, hey, it's written in this form. Well, who is C and who is b? And so in your head, over 2 pi. What's 4 pi over 2 pi? 2, right? But the other way is that you could actually say or see that this is written in a weird way and be like, oh, I wish it was written like this because C over b is super easy. We could have rewritten him at the very beginning and said, oh, I don't like the way he's written. So instead, I'm going to pull out the 2 pi. And if you pull out or if you factor out this constant, which is b, pulling him out to be in front, what would be left inside? X plus 2. When you factor, you divide. So pulling out a 2 pi from him, it's gone. X remains, 1x. And then dividing by 2 pi, 4 pi over 2 pi is 2. So either way, you should end up with a, wait a minute, is it a plus 2 or a minus 2? If the formulas have a minus, just like horizontal translations had, it's backwards of what you think. If we see a plus, what should we be thinking over here? It's a minus. It's moving left. So now that we have it factored, and maybe more of you can see why it's going to be the number 2, or it could be C over B, which will also be 2. We just have to realize, oh, wait, it's a negative because it's backwards what I think. So this is us, number 3, looking at our C over B. I guess I don't really need to number it over here because we're numbering as far as which clue that we're trying to find or identify. But what does this say about the y value? Y. Who's D again? D is the sinusoidal axis, and then A is the amplitude. So sine is saying start at the sinusoidal axis, and the sinusoidal axis is the middle. And cosine is saying start at the sinusoidal axis plus A. Well, that's weird. Maybe we should go back really quickly and remind ourselves of who is sine and who is cosine. Where does sine normally start at? The middle. And where does cosine start at? The top, or the max. So that's why those initial points are what they are, because sine does start in the middle, and if it's not transformed, it's y equals 0. And cosine does start at the top, and if it's not transformed, it's 0 plus 1, or 1. So over here, once we have the transformation, if it helps, I don't know if it will, but you can actually put here and you could say the middle is where sine starts and the top is where cosine starts. But here's the trick. Why am I going to put 1 instead of 7? Shouldn't it be 7? Shouldn't it be the top and the top is 7? 3 is negative. Does that make a difference when you have a negative that's being multiplied by something? It's a reflection. So, hold on. If I were you and you still have that colored pen, super particular point of this minus. Because the one thing that we don't really talk about here is what if there's a minus? Look, all of these are plus, 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 plus. You might want to make a little note to yourself that if there's a minus cosine, a negative sign, you have to think of, uh-oh, the graph has been reflected. And not just any reflected, it was, or it has been reflected. So if cosine usually starts at the top, but it's been flipped, I know this is a little bit tricky, but remember, we've already made our middle, our top, and our bottom of our wave. So if it's been flipped, it's not going to start at the top. Where is it going to start? At the bottom. So that's why I put the 1 there. That's not how cosine always is. So we need to make a quick little note of that, that in this one we went ahead and started on the bottom, but only because there was a vertical reflection. So we had to flip it. All right, no big deal. Make your wave. Huh? Is that it? Maybe. Is that it? Maybe. Is that it? Maybe. What don't we know? We know how high, we know how low, we know the center, we even know what cosine looks like, and if it's a vertical reflection, we even know, I don't know why that's selecting things randomly, we even know, in general, it's like bell-shaped, a downwards wave, but we don't know how wide to make it, because what's the one thing that we haven't looked at yet? Okay, so then coming over here, after we figured out how high, how low, and where our little wave, and specifically which wave we're talking about, starting in the middle or the top flip to the bottom. Now we have to think about, last but not least, the period. So, coming back over here, we need to know how long to make this wave, and how long to make this wave is what we call the period. What's the period? Can you guys look in your notes at the very beginning of notes? How long or how many x's did it take to make one sine or one cosine curve? 2 pi what? Well, that's the formula for period, but in the very, very first sine and cosine that you guys graphed on the Friday before break. 2 pi, right? Sine, middle, top, middle, bottom, middle. Took 2 pi, and cosine, top, middle, bottom. Both of them took 2 pi. This little guy, 1 cycle, 2 pi, and this little guy, 1 cycle, 2 pi. So when I give you this formula for period, and when I 1 over b times 2 pi or 2 pi over b, what I'm saying is, remember, horizontal dilations, backwards what I think, different than what I think. So instead of multiplying by b, you divide by b. Divide who by b? The normal period. So normal period, 2 pi divided by, what's b again? You can find him here, or you can find him here. It's the same thing, 2 pi. Our period is 1. However, how many need to fit in that distance of 1? I can put a 1 right here, no big deal. I can put a 1 and I can say, okay, from here to here, 0 to 1, that's how long my wave needs to go. But I need to go not just from bottom to bottom, but aren't there points in between also? Okay, there are 5 points total. So if there are 5 points total and I already know the beginning and end, how many points am I missing? 3. So I have the beginning, there's 1. I have the end, there's 1. I'm missing 3. I need to section this off into 3 equal subdivisions. Uh-oh, wait, that's only 2. Splitting into 3 only gets me 2 key points. I actually need, what would those units be? How can we figure that out? If I need to put 3 more points, I need them equally spaced. Don't divide by 2. Divide by 4. Good. Every period needs to be split into what we are going to call quarter cycles. And quarter cycles, you just take a period and divide by 4 and say, hey, what are my units? Oh, my units are... So 1/4, 1/2, 3/4. And I'm going to go middle. No, bottom, I apologize. Bottom, middle, top, middle, bottom. They want 2 cycles of cosine. How many cycles is that? Just 1. So we could go ahead and go this way. Oh, I ran out of room. So what can we do instead? Let's go backwards. But the nice thing is, don't I just need to keep on going by quarters? Then I can keep on putting my key points as long as I remember I have to always hit each of my guidelines along the way. Now, in reality, is this like a really spread out wave or a really squished together wave? It looks spread out, but why does it look spread out? Yeah, we did what? We made the unit by 1/4. If you guys were doing your graphing calculators right now, Zoom standard is -10 to 10. How many of these would fit? Like 20 of them. So it's really squished in. Because remember, the original period is 2 pi. And what's 2 pi as a number?
Like 6.
6-ish, right? So my 6-ish became 1. So what happened to my wave? So when you make the waves on your paper, just be careful, because all your waves, as long as you do your own way, they're going to be kind of the same. Yeah, they might be shifted here or there. They might be stretched here or there. But you're going to make your units make it look like a normal wave. But if it was like on a 10 by 10 grid, it's going to be like the waves are really squished together. So don't lose the context of what's going on. But do you guys see how we did 1, 2, 3, 4 done? So let's try again. But before we try again, let's talk and make sure that you know what each of these little pieces are. Because you're going to see some of these words in homework. I just want to make sure that you're tracking with who they are, what they are. We call them the characteristics of sinusoids. First one, amplitude. Is that fitting? My projector got weird. It's even leaving off more on my screen. Amplitude, how high, how low. I've said it, just you guys haven't written it. It's how high or how low the graph goes. But it's technically half the distance. Because remember this wave over here? It's actually, from top to bottom, it's actually 6. But we're thinking about from equilibrium or from the sinusoidal axis. Remember, say it like you're from Jersey. I was in Jersey over break, but only for a couple hours. My friend lives in New York, but the airport in Jersey is a little bit easier to get to. You can pretend you're in Jersey. Go to Jersey Mike's. But anyway, sinusoid, right? Sinusoid. Amplitude, half the distance between the max and the min. Half the distance from the sinusoidal axis to the top or to the bottom. But that one kind of makes sense, because at least you guys, most of you have heard of amplifiers or amplify or amping up the music, etc. Period is a little bit harder. But we're thinking about cycles from the beginning to the end of one cycle specifically of sine and cosine. It's how long it takes, like a period of time, like a time period. And so we're talking about the horizontal distance from beginning to end. And as you guys noticed a second ago, I had almost all of this figured out, and I still couldn't make my wave. Even after I knew the first point. Without the first point, I'd be stuck too. But I still couldn't make my wave because I didn't know how long to make it. And that's something that comes with practice. You can think over here, and if I was just to give you these lines as like a little baby kindergartner, or maybe something in preschool. Usually kindergarten, though, is when you start doing this, first grade. If I just gave you these lines and like, hey, use it, you'd be like, I have no idea what's going on. I mean, I'm sure you could draw something. It probably wouldn't be what I wanted, though, right? Which is why they had to give you the dotted letters and have you trace the capitals and the lowercase and trace it a few times to get the feel for it and then try to do it on your own. It was pretty gnarly, I bet, when you started. These waves might be a little gnarly, too, but as long as we have our guidelines, the sinusoidal axis, the amplitude, the period is what's going to help us know exactly how long to make this. And you shouldn't be putting any x values until you know the period. Because if the period was 20, I'm not going to want to go by ones or 1/4. If the period was 1/4, I'm not going to even want to go by 1/4. I'm going to want to go by 1/8. So I have to be careful and consider the period before putting any x tick marks. Beginning to end of one cycle. And you can think, if it helps, for a sine, for a cosine. I'm just doing a sine as an example because we just did a cosine. When you're trying to get your wave, beginning to end is the period. But how you split up, how you make your units on your axis, those are going to be the quarter cycles. Which this one was super basic because literally if the period is 1, then the units were quarter, quarter, quarter. But as soon as the period is something other than 1, well, the quarter cycles are going to be a little bit messier too. There are 2 more. But they both fall under the exact same category of translations. There are 2 more, but they both fall under translations. So far, we've used A. We've used P. We've used 2 pi over B. Remember, A is the absolute value of little a. But who's the vertical shift? We have two letters we haven't used yet, D and C over B. Who's who? Is D vertical or horizontal, Joe? D in this one was 4, and C over B was -2. Ooh, does anybody notice something that went wrong? Which one's vertical? Vertical is going to be D. I actually just noticed a mistake that we totally disregarded. I totally disregarded. But really quickly, vertical shifts, that's Y equals D. If the center of this guy moves, that's a vertical shift. If it's not on the x-axis, if it's somewhere else, that's a vertical shift. So that's going to be our sinusoidal axis. That's how we deal with vertical shifts. Can I show you guys a quick little hint? If you were to ever see y equals 3 sine of pi x minus 1, who's your d? Not 1. There's no d. What do you mean? Isn't d the number that gets added in front? Oh, wait. There's no number added in front. So who is d?
0.
Yeah, so d equals 0. So does this one have a... No. So quick word to the wise. We are looking for sinusoidal axis, which is usually there. But if it's ever not there, if there's nothing being added or subtracted in front of your sine or cosine, then the d is always 0, meaning it hasn't shifted vertically anywhere. So you could put your little middle of your wave, your equilibrium, your sinusoidal axis, just put it on the x-axis. Leave it there. Horizontal shifts. Okay, hold on. This is our initial point. And horizontal shifts, that's our last one, which is going to be x equals c over b. You can call it your phase shift. I wanted you guys to have that wording. The horizontal shift, the phase shift, the shift for the beginning of the cycle is c over b. And so for us to double check our example, make sure that everything is good, that that wave is perfectly the way that we want it, we need to go back to our example and make sure that each of these have been identified. Amplitude, do we have the right how high, how low? Period, do we have the right beginning to end length? Vertical shift, did it go up or go down if it needed to? Phase shift, did it start where it was supposed to? Let's check it. Sinusoidal axis, did it get shifted up 4? Yeah. Amplitude, did it get stretched to go up 3 and down 3 from that middle? Yes, it did. Period, did it begin and end in the right time? Uh-huh. Initial point, did it start where it was supposed to? Where did I start it? 0, 1. Where was I supposed to start it? Uh-oh. So where's -2? Isn't this -1 only? 1/4, 1/2, 3/4. Uh-oh. Let's see if we're really in that much trouble. We're in trouble if we have to change the whole thing, right? 10. What happens if I keep extending? Is this going to be okay after all? That wasn't my axis, I apologize. Sometimes it's easy to get the bottom confused with the axis. Hold on. Am I going to be okay? Because what's going to happen if I keep going? Where is it going to hit? Yeah, so actually we're lucky we're okay, but are you usually lucky? And the answer is no. All right, kiddos, we have a nasty example. But we didn't get to our homework helps, so I'll make you a deal. I want you to try to get at least halfway through homework for your Google Classroom submission. Sound good? Yeah. All right. See you guys tomorrow. Get at least halfway. If you get stuck anywhere, come with questions. We'll finish up our homework helps tomorrow. Don't forget your corrections.